Hello guys, today we are going to start double integration and we are going to ask most important problem from the physics perspective as well as IIT JAM and JEST perspective. So in the previous video, I have talked about how to find the double integration using Cartesian coordinates, and when I try to say Cartesian coordinates, I mean x, y, and we found that we can easily find the area of some region using this technique, that where you are going to use the double integration and the integration on x as well as dy, and from there you can easily find out the area of integration or area of the region. And we have also discussed that suppose you have any particular function, and in that case we have talked about the prism, how to find the air volume of the prism. So you can just take write this particular area integral using some function f of x comma y, which is defined for different kind of regions, and then you are going to again integrate either dx dy, or you can integrate dy dx. Just a little bit of recap. I have already told you that whenever we try to find the integration, we first choose that in which portion we are going to integrate. Suppose that you are first taking the integration with respect to x. It means that here y is constant. And when your y is constant, then you are taking the integral like this. X is equal to g1 of y and x is equal to g2 of y. Okay, so this kind of things are coming when you have the region which is not rectangular, maybe some kind of ellipse, or maybe some kind of this type of functions where your x and y both are dependent and so on. So you have to first change your integration as x is equal to g comma y and x is equal to g to y. On the other hand, if you are following this integral where your x is first integral in which x is constant, then you have to express the y in terms of x. Let us say h1 of x, and then y is equal to h2 of x, and then you can evaluate the integral in terms of dx. Now here we are going to again follow some particular problems. Let's say that suppose you are finding a region, you are making some kind of region, and you want to find the area due to this region. For an example, there is a region, there is a region which is bounded by y is equal to x and y is equal to x square, which I have already discussed in the previous lecture. So you have to find the area in first quadrant. Area in first quadrant. How are you going to do it? We understand what is the y is x square. Y is x square is kind of parabola. And when we are plotting y is equal to x, it means that the slope, it means that the integral, the constant is on the 0. Therefore, this line is going to from this 0, 0 line to at some point. Now we understand that since x is equal to 0, y is equal to 0, it will give you 0, 0. Okay, so one of the limit is, one of the coordinate is already fixed. Other coordinate can be found just by since this curve and this line is meeting on at some point, it means that these two are at this point will be same. So how we can find? We can say that for the line and the curve has to be equal in order for this particular point, not these ones. Okay, so I know x minus x into x, x into 1 minus x. If I am taking this side, 1 minus x is equal to 0. Therefore, x is equal to 0, x is equal to 1. So if you put x is equal to 0, you're automatically y gonna 0, and x is equal to 1, y is 1. So I know this particular point. Now we have found that due to this line and the parabola, we have this particular region. Therefore, I have to find the area of this particular region. So I can just simply express that. Okay, what I can do is that I can take an integral first, x my constant, and I'm going to do this integral in the y, and then I'm going to stretch this integral over x. So how we can do? We can do just by putting dy and then dx, because I am first finding the integral in the y respect, because this is a y coordinate and x. And for here, because why it is easy, because we have already given that what is y is equal to x, y is equal to x square. So I'm just writing here y is equal to x and y is equal to x square. So here my x is constant. So I can just simply say that this integral will give you what? This integral is going to give you x square minus x, and now you have x. Now you have to again put what is your x integral, or what is the x limits. The limits x is going from 0 to, it is 1, because here it is your 1. So that's how you can make this particular region. So I'm just going to integrate 0 to 1. And here is your answer, x cube over 3 minus x square over 2. Put the integral 0 to 1. So 0 is going to, 0 will be no change. So I'm going to get 1 by 3 and 1 by 2. And 2 minus 3 would be 1 over 6. Okay. So this is how we are going to, going to able to find the integrals. And just for this, sorry, oh, wait a second. When we are trying to do the limits, you have to go from upper, sorry, this region to this region. And this line, this basically this integral is cutting this y is equal to x square line. So this has to be y is equal to x square. And then you have this one, x. So yes, I can write here negative of this one. And this would be negative of everything. Negative of everything would be minus 1 and this one. And then how we have 1 by 6. In first place, I have not written minus of 1 by 6 because I know that area cannot be negative. So it means that we have done something wrong, and here is the wrong. So when we are taking the limit, you have to first go from below to above. We have already explained in this previous chapter or previous video. You can easily find it out. Now, the most important topic that we are going to talk about today is how we can find the average value of any particular, let us say, particular function and so on. So consider that there, we have already done in class 12 or so on, that suppose you have a wave kind of, characteristic. Suppose there is a wave equation, and you know that this wave is going from 0 to, let us say, this is your pi and this is the 2 pi. Or we can say that this is the from 0 to pi, this is the particular, time limit. That is the total cycle. To complete one cycle, the time period is t. Okay. And similarly, this whole cycle is, repeating its after some interval, and whole the time period is coming out to be t. Now, for an example, if you try to find out the AC, okay, in the AC current, alternating current, we have current can be given by I naught cos omega t, where omega is angular frequency and t is the time. This is the t, and this could be I. So there we have to find that what could be the average value of this this current. Understood? Because average values are very much important. So whenever you have the wave characteristic or any kind of function, just like in quantum mechanics used to do that, what is the average value of some particular function? Understood? So for an example, you have some particular function which is only depend on, let us say, t, because just like I is depending on only t, and where omega is constant. So if f is depending on t, it means that it is a one-dimensional variable. Okay. And in order to find the average value, I'm just doing f, and these are the angular brackets, and this is denoting that average value of f. And this can be done that what is the how the function is changing over this particular interval, just like 0 to t. I'm going to write f of t times dt. Okay. And then what is the total time period? Means that the total time period is 0 to t. So 0 to t and dt. This is how we can easily find out the average of any function at some particular interval. So similarly, you can do for this one and this one. Now in 2 dimension, we are going to just extend this idea that instead of instead of one variable in 2 dimension, we can say that f is depending on x comma y instead of just 1. So I can just find out the average value of this particular function can be determined by 0, sorry, not in some particular limits. So I'm going to first do it fx comma y. Let us say I'm writing it in dx and then dy. And then again, I'm going to find the area of this particular region like dx and dy. Okay. So if you have taken this one as like this, so you have to, and we have already told you that, if you are changing this and this, the integral will not change. The final value of integral won't change if the function is already continuous. So what does it tell? It tells that whenever you try to find out the average value of any particular function, which is depending on 2 independent variable, then you have to normalize that particular volume with respect to the region, because we have already told you that in case of when you are writing some function in the area integral, it will give you some kind of volume. Okay, the volume of the complete region. Understood? So the for the volume, that volume need to be normalized with respect to the area. So this is the kind of very um, standard technique to do it. Similarly, you can do it for the 3D integral and so on. So if you understand this kind of particular trick, then in quantum mechanics, you won't have any problem to determine the average value of some any operator. Understood? Or any region. Just like in energy, we have to find it that in terms of how to find the average value of momentum, or let us say average value of energy and so on. So this is the technique that you used to do. And in the quantum mechanics also, the variable is, all the operator is depending on just only one variable. So we are going to use that technique, and over here we are going to use this one. So in that case, this is the normalization constant or normalization quantities at which, so that the probability must be equal to only one. So we are don't, in quantum mechanics we don't care about different things. We are just caring about that the maximum probability that can any event generate is just one. Okay, so this is it. Now we are going to so just before I'm going to do more topics, let me just choose one particular problem, that find the average value of some function. Let us say f of xy is x cos of xy over a rectangular, over a rectangle whose x is given by like this one pi, and y is given by 0 to 1. Okay, so I can simply say that I first try to find the integral of x comma y and dx or dy, whatever you can assume. Okay, and now since you can already see that these integrals are not changing, not depending on something, so what I can just write, I can simply say that x cos xy. Okay, now since x is depending on also cos x is depending on xy, and it is multiplying with also x, so what I can do is that instead of choosing dx to be a variable, I'm going to choose dy, and then I'm going to do it dx. Okay, so that things are not too much complicated. So over here, if I'm choosing this one, so this will be 0 to 1, and then this integral will be 0 to pi. Okay, so x dy, so this will be giving you x sine xy over x, because for this x becomes some constant, and the integral of cos of alpha x, where alpha need to be taken downstairs, and you're going to put the limit 0 to 1, and then I'm going to put 0 to pi and then dx. So over here you can see that sine of xy, x times 1, and sine of 0 is again 0, and you have the integral 0 to pi and dx. Now sine x is negative of cos x, and negative of cos x 0 to pi will give you -2. Okay, sorry, not -2, it has to be +2, because area, we're finding the volume. So therefore the function that is inside this particular region, okay, which will have the volume would kind of 2, and then again we can find the area by using this one dx and dy. Dx is from 0 to 1, and dy is, sorry, dy is 0 to 1 and dx is 0 to pi. I hope I'm correct. Yes, so 1 times pi. Okay, so the average value of this particular function would be 2 over pi. So this is how we can easily find out, for any function we can find out the average value of that particular function. Now in the next topic of the video, what I'm going to question that, what if we have some complicated feature? What if we have some symmetry in our nature? For an example, when you're talking about the symmetry, it means that if you take any object and you translate it, this object is not changing. You can say that this object in the linear transformation won't change. So it has linear kind of symmetry. So we can say that, okay, fine, this you can think about a rectangular coordinate or x comma y kind of thing. On the other hand, suppose you take any object and you try to rotate it, and by rotation this object is not changing its configuration, then we can say that it has the circular kind of symmetry. Understood? Now when you have circular kind of symmetry, then everything can be transformed in this coordinate r comma theta. This is called the Cartesian coordinate can be expressed in r comma theta, and this type of coordinate we can say that polar coordinate. So if any particle over the circle, we can simply say that, okay, in order to solve this type of problem, we can say that, okay, what is the Rx? So I can say that this is x is equal to r of cos theta and y is equal to r of sin theta. And if you do this, then your problem will automatically solve, because if you do x square plus y square, then you will find r square, and tan theta will be simply y over x, and you can have the more relation like theta is equal to tan inverse x over y. Okay. So before we find that, okay, maybe there are something we have, maybe have some kind of symmetry, and we must need to do the this kind of job. For an example, let me give you an example like sine of x square plus y square, and let us say it's going to have dx dy. Okay, so now you may see that the sine of y square or sine of x square, if you say that, okay, y is constant, then it's itself a kind of a challenging job to find this integral. So what you can just do that we can change in terms of polar coordinate. So what we can do that x square plus y square will give you sine of r square. So you can say that this has now become sine of r square, and this on the other hand, this will again will change and so on and so forth. Okay, or maybe we can say that it is kind of square root of x square y, and then this will give you just only r. Okay, but how we not change the dx and dy? So in the that is the thing we need to focus, that how we can convert the Cartesian integral into the polar coordinate integral. But before doing that, we are just first taking the polar polar coordinate form, and in this polar coordinate form we are trying to evaluate that how we can express the double integration in terms of polar form. Okay, so usually the polar kind of integral is coming from the circle. So as you can see that if you have circle, then it has radius, and it has the radius, let us say r, and the theta is changing. So you can go from here to here by just changing that angle. And suppose you have concentric circles like this, this, and this. By changing the r, you can go from one circle to another circle. So it means that if you want to jump on the linearly, so you can vary r, and if you jump from some orientation, you can vary the theta. So it means that your dx and dy is going to convert in some r and d theta. Okay, r and theta. So the linear can be done by r, and the angular variation can be done by this one. So in the double integration format, what we can express that you just have to require dx times dy can be expressed in terms of r dr and d theta. I'm going to show you in a minute that how we can do it. So before I'm going to jump on the particular thing, like how we can write the double integration, let me just give you an analogy that suppose I have a disk and I want to find the area of this particular disk, area of a disk. How will I do? So again, disk is a circle, but in the disk, what you have some material from center to all this line. So for that purpose, what we can say that, okay, since each and every section is filled with the material, I can say that let us say the radius of this disk is r, and for an example, say since everywhere there is a material, what I can say that, let us say particular r with particular theta, I can choose some particular kind of material. So how we can choose? So let us say I can choose that at this r we have this much, and if I'm changing the angle by theta 1 or theta 2, so I have this infinitesimal theta, let's say d theta, I will have this one. Now since in this disk I can move from center to this one, so I can say that when your r is this much, then you have this particular what you can say the sector, and just since I can go from back and forth, I can just go over here and over here. So it will make some kind of if it is a very smaller, then the disk can be think of as a rectangle, isn't it? So this thing is like dr. Okay, so this one is dr. Now over here you have this one d theta, So this is making an kind of angle like d theta. So I know what is this one, how we can write it, because I can say that this d theta can be written as from here to here. I can say that this particular thing is r. So d theta is equal to this particular length. Let us say this particular length is what? This particular length, let us say L, and over here r. Okay. So that is how we can find out the for the any kind of curve, that you have any kind of curve, then you can find the length of that curve by using this technique. So therefore this length will become r d theta. So this is now become r d theta. Okay. So since this is a rectangle, what is the area of this small curve? This small will be this one, this length into this length. So this length would be dr times r d theta. That's why we say that whenever you have to find, whenever in area integral in the Cartesian coordinate, we have dx dy. So dx dy would be converted into dr into d theta. So here how we can find the area? The area is this particular region. So area would be r dr times d theta. Now since we have particular theta would be constant, so theta would be like, okay, we can always go from 0 to let us say 0 to 2 pi, because so whenever we try to find the integral, we can just make one particular line, and here it has 0. Okay, and since this line is having it's cutting from in the linear direction, so first it is 0 and it is cutting at distance r. So the first integral will be r, and since we have plotted in the view of some particular constant, that is theta, and theta can be moved from here 0 to, again the whole circle would be 0 to 2 pi. So that is how we can do the integral. So I know that r dr would be r square by 2, therefore this would become r square by 2, and the theta will become 2 pi, so this is 2 pi. So this is how we can plot pi r square. So the area of disk is pi r square. So this is the way we can find out the area of our disk. Now same analogy can be fit, that if you have any kind of function over some particular region, then I can just write the area as integral f of r comma theta. First I am going to do this dr. Well, I have to write r dr, because this is how we can find out r dr. Wherever we will go, you have r dr and then d theta. So first I have something, because suppose it is not, it's a circle, but there are different kind of curve exist in the polar form. So r is generally depend on, let us say, g1 of theta, and r would be g2 of theta. And here the theta will again maybe vary from, let us say, theta 1 to theta 2, and these are constant. So this is how we can easily find out. I'm going to give you some particular limits, and I'm going to show you that how we can give you a particular, how we can find that if the region is not circle, something else. So there is a problem that find the limit of integration, find the limit of integration. There is some function, let us say f r theta, over a region r that lies inside the chordoid r is equal to 1 plus cos theta, and outside the circle whose radius is 1. So when you have the chordoid, how the chordoid looks like. So if you are a YouTuber or someone, so when you are using the mic, when you go to purchase a mic, there is a they will ask you that you want omnidirectional mic or the chordoid version. It means that the mic can can capture the sounds not coming from only unidirection, but it can capture the sound from the each direction. Okay, so suppose there is a 1-to-1, suppose here I am and opposite to me there is one person, then we have the chordoid version of the mic settings, from where that simultaneously it can capture my voice as well as the person that is sitting opposite to me. So that is the real life application of this chordoid thing, and you can see the chordoid is kind of like this. This is how the chordoid looks like, and the chordoid curve is given by r is equal to 1 plus cos theta. So this is it. Now we have already the background function is x comma y, and the theta is like r is theta, like we have this particular coordinate. So you can easily plot it how it is look like in r is equal to 1 plus cos theta. This is the version. where your r and theta is varying. Okay, so how we can say that r is varying? So here, if you take a line from here to here, so you can see that by varying this angle, you can go from here to here to here, and you can see that if you go this side, your r is changing and your r is not constant. Just like in the circle, r is constant, but here is r is not constant, so r is varying with cos theta. Okay, so now you have to make a circle. Now you can already see that if theta is equal to 0, then r is equal to 2. So from here, I can say that if theta is equal to 0, this thing is very big. That is true. Okay. And the minimum thing is cos theta becomes -1, so r becomes 0. So that's why here r is equal to 0. So that's why it is landing over here. Now, when you try to plot, and 1 could be, let us say 1, and there is a circle of radius r. So circle of radius will become like this. Okay, this is maybe circle. So now the thing is that will this circle and the chordoid will intersect each other or not? So I can simply say that the circle of radius r is 1, and 1 plus 1 cos theta, I can write here 1 is equal to 1 plus cos theta, and hence I can write, since cos theta is 0 degrees, so theta will become plus pi by 2 and minus pi by 2. So in this plus pi by 2 and minus pi by 2, they will intersect. So this plus pi by 2 is over here and minus pi by 2 is over here. My drawing is bad, that's why you cannot see over here, but this is this. Theta at theta pi by 2 and minus pi by 2, it will cut. Okay, so now you can see that the circle is over here, and they have already said that, find the limit of integration f of r theta over a region r that lies inside a coordinate r is equal to 1 plus cos theta and outside the circle. So what is the region that is outside the circle? Outside the circle is over here, and inside the coordinate is here. That is the intersection of this one. Okay, so this is the region, the area we have to find the area of this particular region. Okay, so how we can find the area of, I can simply write area would be, first I'm going to do here rdr. Okay, rdr, and r will going from, now we have to choose the limits, that which limits I'm going to prefer. Now from here we can say that this thing is, first I'm going to determine this one theta. Okay, so this theta, this region is bound from here to here, so this theta is capturing this angle minus pi by 2 to pi by 2. Okay, now over here rdr, how we can choose rdr? So if you make any angle from here to here, so what we can say that first it will intersect this one from entering to outside. Okay, so this is the circle has radius r is equal to 1, and then it is going towards this this region which is on the r is equal to 1 plus cos theta. So I can just simply write r is equal to 1 plus cos theta. So this is how we can determine the limits, that just to make a one line and where this is cutting. So this is the region that we are interested. So the lower limit would be here, and this is on the circle. So on the circle r is always 1, and on this on this cardoid, because any point on the cardoid will satisfy this parametric equation. Okay, that's why I'm just writing r is equal to 1 plus cos theta. Now they have said that this f of r theta, okay, find the limit of integration f of r theta. Now here you can see in this example, what is the f of r theta? F of r theta will come out to be 1. Okay, so now since we are just finding out the region, therefore in this case f of r theta will also become 1. Understood? So we are not particularly taking any kind of prism that we have, when we are talking about f r theta, so something is evolving, just like if you have piles of circle, if it will yeah, piles of circle, then it will make a cylinder. So you have some particular area, but at which the height is building on. So in this case, you can say that the z factor or the height is f of r theta. So in this case, the height is not depending on this r and theta, it is independent. So you can just say that, okay, this is the particular height, let's say 5 centimeter, and you will find out the volume of the cylinder. Understood? So here we are going to do that. Okay, since nothing is building up something, so we are not going to get any height, we are just finding the area. So f of r theta is just pretty much constant. So here first of all r square by 2, and r square by 2 will given by 1 plus cos theta, then 1 plus cos theta square, and then 1, and then we have to take an integral. So I am not going to interested on doing this one. You can easily find out what is the answer. Okay, now as I have already discussed you that how we can change the coordinates of x and y, and there is I am going to give you a particular example, that suppose somebody has already given you the integral in the Cartesian form, let us say f of x comma y and dx dy. I have already said you that this xy just will give you x becomes r cos theta, that is the thing you have to take, and r sin theta, and dx dy becomes r dr and d theta. Okay, so this is how we can change any Cartesian area integral into the polar area integral. Okay, so in order to evaluate, I'm going to take one particular example. For an example, you have this one, e of x square plus y square and dy times dx. Now you may see that e to the power x square is again kind of very much very difficult one. So I can just write here x square plus y square. If I put x is r cos theta, y is r sin theta, therefore r square, and dy dx will give you r dr and d theta. Now they have asked you that this integral is bounded by, they have already asked that this integral is bounded by the curve y is equal to 1 minus x square. Okay, so and this region is semicircle. So it means that you need to plot a semicircle. Now you have already seen that the radius is, in order to find the radius, you know that x square plus y square is equal to r square is the parametric equation of circle. So here you can see that radius is 1. So from here to where it is 1, understood, 0 to 1. And now what you can see that, for example, if you have any particular, how we can find the limits. In order to find the limits, what you are required that this radius is going from 0 to 1, because just plot a line 0 to 1. What about theta? Theta will go to this 0 to pi. So it is pretty much very interesting, not a very hectic process. How we can find the integral? Let us say r e to the power r square dr. First I'm going to plot this one. Consider t is r square, so dt is 2r dr. Therefore r dr becomes dt by 2, and e to the power r square is et. 0 to 1, I'm not changing this limit for now, and you can easily find out that exponential of et is just et, okay, by 2, and 0 to 1, et is e r square by 2, 0 to 1. So here I have e by 2, no, e minus 1 by 2. So you see that e to the power e minus 1 by 2 is the first limit, and now d theta from 0 to pi, and you got e minus 1 into pi by 2. Now you may think that e to the power x square, again this is this is the Gaussian integral, e to the power x square plus y square. It is kind of a very hectic job in order to find it, but you see that using the polar kind of manipulation, this is just a very little problem from the perspective of any class 12 student can do this kind of integral. So you see that is the magic of double integration. When you try to change something from one coordinate to another coordinate, you have to first think what is going on, what are the important variables, and then so I'm going to summarize this everything, because there are so much thing we have already seen in this video. So the summary is that if any function that is depending on this kind of x and y two variables, and we try to find out the average would be like, just take an integral in dx dy and you do the area integral over here on this region. Now area of any region given by dx and dy is this the area, understood? Now we can change from Cartesian to polar by going x is equal to r cos theta, and this r is need not to be constant, as we have already seen. In order to find the area of disk, y is equal to r sin theta. Dx just can be dx and dy, okay, I cannot just write in separately, can be written as r dr d theta, not dr into d theta, r dr d theta, and we have already seen that how we can write it. And so area in the polar coordinate can be written as f of r comma theta r dr, and then you have to express everything in terms of, let us say, g of theta and g2 of theta, and there is theta, and this theta will have some particular coordinate over here. Okay, and now if you have this particular x comma y dx and dy, I can convert it into f of r cos theta, r sin theta, r dr, and d theta. Now, and in case of f of r comma theta, I can easily find out the average value of this function just by doing f of r theta, r dr, d theta over on the region r dr, d theta. So this is the total summary of today's lecture. We have started from this area integral, how we can find the area of region. We understood that how to take a limit. This thing is very much important once you have decided either you want to do the integral with dx and dy. So I hope everything is clear, and in the next video I'm going to do the volumetric integration, and this volumetric integration is much important because you can understand that we have different symmetries, and the symmetry on the sphere is kind of very important one, and you can easily solve so many problems using the volumetric integration without going in complicated. So many times it is happening that if you do the integral in the Cartesian coordinate is very hectic process. That's why we have to convert the Cartesian integral in terms of polar form, and then we are seeing that what is the next version of the polar form and so on. So I hope you have enjoyed this video, enjoyed this lecture. So मेरे इस वीडियो को, so you can share this video to your friends and ask them to subscribe. We will cover the whole physics, which will be important from the perspective of IIT JAM, JEST, CSI, as well as I have a research channel in which I am simply talking about the research. So if anyone is interested to start his career on research, he can watch the videos on how to use the field general relativity, how we can do the inflation, also how we can deal with the dark energy, dark matter situation. So these are the research problems. I have already made the videos on my research topics, which I am currently working on, and also I have also explored the people who is actively doing the research on this particular field, inflation, what Big Bang, as well as dark matter, dark energy, and so on. So you have to have little bit information about general relativity, which I am going to do in this video. So don't worry, but it will take a little bit time. But if you are really interested at how to do research, how people do research, and you want to start your early career on research and try to get a publication, then you will find each videos how to read research papers, write research paper, and so on in my different channel. You can check out my homepage, and then you can go to that particular channels. Thank you very much for having me. So please subscribe my channel. See you later.